Welcome to Still Science Lab. Tonight, we are going to dismantle the most famous, the most controversial, and the most misleading headline in the history of modern science. We are going to talk about the God particle. If you have ever opened a newspaper, watched a science documentary, or scrolled through a newsfeed, you have seen this name. It appears in bold, terrifying letters. It suggests something ultimate. It implies that physicists have finally drilled down to the bottom of reality and found the fingerprint of the divine. It sounds like the bridge between the cold, hard equations of quantum mechanics and the warm, mystical questions of theology. It promises that if we find this particle, we will look into the face of the Creator. But tonight, we start by tearing that promise apart. The title, the God particle, is not a scientific classification. It is not a theological statement. It is a joke. And not just a joke, but a marketing stunt that spun wildly out of control, much to the horror of the very people who dedicated their lives to finding it. To understand what this particle actually is, and why it is so fundamental to your existence, we first have to clear away the fog of this nickname. We have to understand why the scientific community generally despises this label, and why the true story of its naming is a comedy of errors involving a frustrated Nobel Prize winner and a publisher with an eye for profit. If you were to walk into the cafeteria at CERN, the European Organization for Nuclear Research in Geneva, and shout the name, the God particle, you would not be met with reverence. You would not see scientists bowing their heads in prayer. You would see eyes rolling. You would hear groans of exasperation. You might even be politely asked to leave. To a physicist, calling the Higgs Boson the God particle is like calling a surgeon a miracle worker. It might sound nice to the public, but it dismisses the decades of hard work, calculation, and engineering that actually make the work possible. It replaces the beauty of understanding with the cheap thrill of a magic trick. The origin of this name dates back to the early 1990s, a time when the world of high-energy physics was in a state of desperation. The scientific community knew that the standard model of physics, the great theory that explains how matter interacts, was incomplete. It was missing a piece. Without this piece, the math didn't work. Without this piece, nothing in the universe should have mass. But they couldn't find it. They had been hunting for it since the 1960s. They had built accelerators, smashed atoms, and poured billions of dollars into the search. But the particle remained a ghost. It was elusive, it was expensive, and it was driving them mad. Enter Leon Lederman. Lederman was a titan of physics, a Nobel laureate, and a man with a sharp wit and a deep frustration with the lack of funding for scientific research. In 1993, he decided to write a popular science book to explain why this search was so important. He wanted to rally public support. He wanted to explain to the taxpayer why the United States needed to build the superconducting super collider, a massive machine designed to hunt this elusive beast. Lederman sat down to write his manuscript. He described the particle as the villain of his life. It was the thing that was hiding from everyone. It was the thing that was causing budget crises. It was the thing that demanded a machine the size of a city to detect. He wanted a title that captured his sheer annoyance, his struggle, and the incredible difficulty of the hunt. He typed out his proposed title, The Goddamn Particle. It was perfect. It was honest. It captured the mood of the entire physics community. It wasn't goddamn in a blasphemous sense. It was goddamn in the sense of a mechanic trying to fix an engine that refuses to start. It was the goddamn particle because nobody could find the goddamn thing. However, when he sent the manuscript to his publisher, the reaction was immediate. You cannot put a curse word on the cover of a science book intended for the general public. It would offend conservative readers. It would limit sales. It was too aggressive. The editor, looking at the title with a red pen in hand, made a decision that would change the public perception of science for the next 3 decades. With a simple strike, the editor deleted the damn. The goddamn particle became the God particle. Lederman was hesitant, but the publisher insisted. It was catchy. It was provocative. It played into the ancient human desire to find meaning in the stars. And, purely from a sales perspective, the publisher was a genius. The book, titled The God Particle, If the Universe is the Answer, What is the Question?, became a massive bestseller. It brought particle physics into the mainstream conversation in a way that dry textbooks never could. But the consequences of this edit were severe. The media devoured the name. It was the perfect headline. Scientists hunt for God particle. Machine built to find God. It transformed a scientific endeavor into a pseudo-religious crusade. It created an expectation that finding this particle would prove or disprove the existence of a higher power. Religious groups debated it. Atheists used it. Philosophers pondered it. And in the middle of this media circus stood the physicists, holding their clipboards, trying to explain that, actually, it's just a boson that governs the electroweak symmetry breaking. And please stop asking us if we have found heaven. The irony is particularly sharp when you consider Peter Higgs, the man after whom the particle is actually named. Peter Higgs is a theoretical physicist from the UK, a mild-mannered, incredibly humble man who prefers the quiet of his study to the flashbulbs of the press. He is also a staunch atheist. He has famously stated that he detests the name the God particle because it conflates physics with theology, and he worries that it offends people of faith while simultaneously misleading people of science. Imagine dedicating your life to a rigorous, mathematical description of the universe, only to have your life's work branded with a name that represents everything you tried to keep out of the laboratory. Yet, despite the hatred from the scientific community, the name stuck. It stuck because it captures something that the dry terminology of physics fails to convey. It captures the stakes. While it has nothing to do with God, the particle is, in a metaphorical sense, the creator of the material world. As we will explore later, without this particle, there would be no atoms, no chemistry, no stars, and no life. It is the architect of existence, even if it is a blind, mechanical architect. But sticking to the name the God particle does a disservice to the reality of what happened. It masks the struggle. The story of this particle is not a story of divine revelation. It is a story of human grit. It is a story of thousands of men and women digging tunnels deep underground, soldering millions of connections, writing millions of lines of code, and staring at screens for decades, looking for a bump in the data that was smaller than a whisper. When we call it the goddamn particle, restoring Lederman's original intent, we get closer to the truth. It reminds us that science is hard. It reminds us that the universe does not give up its secrets easily. It fights back. It hides its fundamental laws behind layers of noise and complexity. The search for the Higgs boson was a fight. It was a fight against technical limitations, against political budget cuts, against the very limits of human engineering. The superconducting super collider, the machine Lederman was trying to save with his book, was eventually cancelled by the US Congress. The goddamn particle claimed a victory there. It remained hidden. It forced humanity to regroup, to cross the ocean, and to pour our resources into a new machine in Europe, the Large Hadron Collider. It took another 20 years after Lederman's book was published to finally catch the thief. So, as we move forward into the deeper science of what this particle actually is, I want you to mentally delete the God from the title. Strip away the mysticism. Forget the idea that we are looking for a deity in the data. Instead, I want you to adopt the frustration of Leon Lederman. I want you to feel the annoyance of a detective who has been chasing a suspect for 50 years. We are not looking for a miracle. We are looking for the glue that holds reality together. We are looking for the mechanism that makes things heavy. We are looking for the reason why you are solid, why you can sit in your chair, and why the sun can burn. The truth is far more interesting than the mythology. The mythology gives you a simple answer: God did it. Physics gives you a complex, beautiful, and terrifying answer. The universe is filled with an invisible ocean, and you are drowning in it. The nickname was a mistake, a marketing ploy that worked too well. But the particle itself? The particle is the key to everything. Tonight, we correct the record. We are not hunting for God. We are hunting for the goddamn particle. And to understand why it was so hard to find, we first have to imagine a world where it doesn't exist. We have to go back to the beginning, to a version of the universe that is terrifyingly empty, a place where nothing can stop, and where the speed of light is not a limit, but a prison. That is where our story truly begins. To understand the true magnitude of what the Higgs boson represents, we must first strip it away. We have to perform a mental demolition of the universe as we know it. We need to turn off the mechanism that gives the cosmos its weight and see what remains in the ruins. We tend to think of mass as a fundamental property of existence, perhaps the most fundamental property of all. You are made of matter. That matter has substance. It takes up space, and if you push it, it resists. If you step on a scale, the earth pulls down on you. This feels like a default setting. We intuitively believe that to exist is to have mass. But the mathematics of the universe tells a completely different story. When physicists first began writing down the equations that describe the fundamental particles, the quarks that make up your atomic nuclei, and the electrons that orbit them, they encountered a stubborn, impossible problem. The math worked beautifully, predicting how particles should interact, how forces should be exchanged, and how the universe should function. It was a symphony of logic, except for one glaring, catastrophic detail. The equations insisted, with absolute mathematical certainty, that the fundamental building blocks of nature should have no mass at all. According to the raw laws of the Standard Model, the electron should be weightless. The quarks should be weightless. The neutrinos should be weightless. In the eyes of the raw theory, mass was not a built-in feature of the hardware. It was a glitch. It didn't belong there. If we trusted the math in its purest form, every single particle in the universe should be exactly like the photon, the particle of light. And this leads us to the terrifying thought experiment, the world of light speed. Imagine for a moment that the Higgs field does not exist. We flip a cosmic switch and drain this invisible fluid from the universe. Instantly, the rules of reality revert to their factory settings. The first thing you would notice is not a change in appearance, but a change in speed. In our universe, there is a strict rule derived from Einstein's relativity. If a particle has no mass, it must travel at the speed of light. it has no choice. It cannot slow down. It cannot accelerate. It is born at the speed limit, and it lives there forever. Mass is the only thing that allows a particle to travel slower than light. Mass is inertia. It is the resistance to change. Without mass, there is no inertia. There is only the sprint. So, in this Higgsless universe, every electron in your body suddenly loses its heft. It loses its ability to sit still. Instantly, every electron accelerates to 300,000 kilometers per second. This is the moment where you and everything you see around you cease to exist. Consider the atom. It is the building block of all matter. It consists of a heavy nucleus in the center, surrounded by a cloud of electrons. The only reason the atom exists is because the electrons are captured. They are held in orbit by the electromagnetic attraction of the nucleus, buzzing around it like bees around a hive. They are fast, yes, but they are contained. They possess mass, which gives them a certain lethargy, allowing the nucleus to reel them in. But in our light-speed universe, the electron is now moving too fast to be captured. It is a massless ghost. The electrical attraction of the nucleus is still there, trying to pull the electron in, but it is like trying to catch a bullet with a butterfly net. The electron zooms past the nucleus at the speed of light, escaping into the void. It cannot be held. It cannot orbit. Without orbiting electrons, there are no atoms. There are just lonely atomic nuclei floating in a sea of frantic, light-speed radiation. And if there are no atoms, there is no chemistry. Chemistry is, at its core, the study of how atoms share and trade electrons. It is the handshake between elements. Carbon bonds with oxygen because their electrons interlock. DNA replicates because molecules can snap together. But you cannot shake hands with someone running past you at 670 million miles per hour. In this world, no chemical bond can ever form. No molecule can ever be built. Biology becomes a physical impossibility. The devastation goes deeper. Let's look at the nucleus itself. The proton and the neutron are made of quarks. In the real world, quarks have mass. But in this hypothetical ghost world, the quarks also lose their intrinsic mass. They too want to fly apart. While the strong nuclear force might struggle to keep them confined, the internal structure of matter would be radically altered. The proton as we know it would likely not exist in its stable form. The universe would transform into a soup. It would be a cold, dark, and chaotic wash of particles, flying in straight lines, bouncing off each other, never sticking, never clumping, never building. There would be no stars, because stars require huge clouds of hydrogen gas to collapse under gravity. But gravity depends on mass. If the particles have no mass or very little mass, derived only from energy, gravity has almost nothing to grab onto. The great clouds of gas would never condense. They would just dissipate, expanding forever into the blackness. There would be no planets, no suns to warm them, no water to fill their oceans, and certainly there would be no eyes to watch it all happen. This universe would be a flash of movement without meaning. It would be a cosmos of pure radiation, a place where time itself behaves strangely because, for a particle moving at the speed of light, time does not pass. It would be a timeless, structureless, eternal storm. This thought experiment reveals a profound truth that we often overlook. Mass is not stuff. We tend to think that mass is a measure of how much matter is inside an object, like stuffing in a teddy bear. But physics tells us that mass is actually a behavior. It is a relationship. It is the measure of how much a particle objects to being moved. And in the world of light speed, nothing objects to anything. Everything goes with the flow of the absolute limit. This is why the discovery of the Higgs boson was so critical. It wasn't just about finding another particle to add to the list. It was about discovering the brake pedal of the universe. The Higgs field is the thing that saves us from the nightmare of the light-speed ghost world. It is the cosmic friction that slows the electrons down, taming them, forcing them to submit to the pull of the nucleus. It allows the electron to become heavy enough to be trapped. It allows the atom to form. It allows the stars to burn. When you look at your hand, you see skin and bone. But what you should see is a miracle of deceleration. You are a collection of particles that fundamentally want to be flying apart at the speed of light. That is their nature. That is their birthright. But they are not doing that. They are sitting still. They are clustered together in the shape of a human being. They have been slowed down, quieted, and given substance by their interaction with an invisible field. This changes our perception of what it means to be real. In the world of light speed, the massless particles are arguably more pure. They are following the path of least resistance. They are unburdened. We, the massive creatures, are the anomalies. We are the ones who are trudging through the mud. We are the ones being dragged down. But it is this drag that makes us possible. It is this resistance that gives us form. The universe without the Higgs is a universe of absolute freedom, but it is a freedom that precludes existence. It is a liberty that results in nothingness. The restriction, the mass, is the creator. This concept flips the script on how we view the physical world. We usually think of empty space as the void, and matter as the solid thing that fills it. But the world of light speed scenario teaches us that the solidity is an illusion created by the void. The particles are just energy. The solidity comes from the field they are swimming through. So, when physicists say that without the Higgs boson there would be no life, they are not exaggerating. They are not speaking in metaphors. They are describing a literal mathematical certainty. If the Higgs field turned off right now, the disintegration of your body would be instantaneous. You wouldn't even have time to register the thought. Your neurons, which rely on the careful exchange of ions, charged atoms, would vaporize into radiation before the electrical signal could cross a synapse. The earth beneath you would disperse into a cloud of light. The sun would cease to be a fusion reactor and would become a burst of scattering quarks. We live on the razor's edge of this reality. We exist only because of a specific, subtle interaction that occurred 13.8 billion years ago. The universe cooled down just enough for the Higgs field to condense, to switch on, and to trap the wild, flying particles of creation in its heavy embrace. We are the trapped ones. We are the slow ones. And because we are slow, we have the time to think, to feel, and to wonder. This realization sets the stage for the true nature of the Higgs. It is not just a particle sitting in a box. It is an environment. It is the water in the aquarium. We have established what happens when the water is gone, the fish die, the glass shatters, the system fails. Now, we must understand the water itself. We must look at this invisible ocean that fills the room you are sitting in. We must understand how a field can be invisible and yet have the strength to hold down a galaxy. We must move from the nightmare of the light-speed void to the strange, thick reality of the Higgs field. This is the mechanism of our existence, and it is far stranger than simple friction. It is a fundamental alteration of the vacuum itself. To understand the true nature of the Higgs, we must stop looking at the particles and start looking at the space between them. We must turn our gaze away from the bright points of stars and the solid lines of matter and look instead at the emptiness. When you look up at the night sky, you see a vast, dark void. We call it space. We intuitively think of space as a container, a blank, empty stage where the drama of the universe plays out. We imagine it as a nothingness, a vacuum that is truly devoid of substance. We think that if you take a box and suck all the air out of it, shield it from all light, and cool it to absolute zero, you are left with nothing. But modern physics tells us that this intuition is a lie. There is no such thing as empty space. The void is not void at all. It is full. It is alive. It is heavy. We are about to enter the domain of the Higgs field. It is crucial here to make a sharp distinction between the God particle, the Higgs boson, and the God field, the Higgs field. The media obsesses over the particle. They show you pictures of the machine that found it, and they talk about the little bump in the data. But in the grand scheme of reality, the particle is secondary. The particle is just a symptom. The field is the disease. Or, to use a more poetic metaphor, the field is the ocean, and the particle is just a single drop of water that flies into the air when a wave crashes. The drop is what we can see. The ocean is what matters. The central concept of quantum field theory, the deepest, most successful theory humans have ever constructed, is that the universe is not made of hard little pellets. It is made of fields. These are fluid-like substances that permeate every single point of space and time. There is an electron field, a photon field, a quark field, and so on. When these fields are calm, we perceive empty space. When you ripple these fields, when you pluck them like a guitar string, that vibration appears to us as a particle. An electron is just a knot of energy in the electron field. However, most of these fields share a common trait. Their natural state is off. If you go into the deepest vacuum of space, far from any stars or planets, the value of the electron field is zero. It is calm. It is silent. There are no electrons there. The same is true for the electromagnetic field. Without a light source, the field sits at zero. But the Higgs field is unique. It is the great exception to the rule. It is the only field in the known universe that does not turn off. Billions of years ago, when the universe was just born, the Higgs field was zero, just like the others. But as the universe cooled, a cosmic phase transition occurred, something similar to water freezing into ice. The Higgs field suddenly broke. It slipped from zero to a specific non-zero value. It locked into an on position, and it has stayed there ever since. This means that today, right now, the entire universe is filled with a continuous, non-stop background hum of Higgs energy. It is everywhere. It is in the space between your eyes. It is in the gap between the electron and the nucleus of the atom. It is in the cold darkness between galaxies. You cannot escape it. If you were to travel to the edge of the universe, it would be there. If you were to build a lead box to block out all radiation, the Higgs field would pass right through the walls because it is the space inside the walls. We are not living in a vacuum. We are living in a submerged reality. We are like deep-sea fish living at the bottom of the Mariana Trench, surrounded by water so clear and so constant that we don't even know it's there. We think we are moving through empty air, but physically, we are trudging through a cosmic syrup. This is the best analogy to understand the Higgs field, cosmic molasses. Imagine the entire universe is filled with a thick, clear, viscous syrup. This syrup is invisible and intangible to our normal senses. You cannot smell it, taste it, or see it, but it is there. Now, imagine trying to push a ping-pong ball through a swimming pool filled with honey. It is difficult. You have to apply force. The honey clings to the ball, drags on it, and resists the motion. This resistance is what we call mass. This is a radical redefinition of reality. For centuries, since the time of Isaac Newton, we thought mass was an intrinsic property of an object. We thought a rock was heavy because it contained rockness. We thought mass was something you owned, like your eye color or your height. But the Higgs mechanism teaches us that mass is not something you have. Mass is something you do. Mass is the measure of your struggle against the invisible ocean. When you try to accelerate your car and you feel the engine straining to push the vehicle forward, you are feeling the Higgs field. The atoms in your car are interacting with the field, and the field is pushing back. It is saying, "No, I do not want you to move." This reluctance to change speed, this inertia, is the direct result of the field clogging up the machinery of the subatomic world. It is important to clarify a common misconception here. The Higgs field is not exactly like friction. If you slide a book across a table, friction slows it down until it stops. The Higgs field does not stop you. If you are moving at a constant speed in space, you will keep moving forever. The Higgs field doesn't punish motion, it punishes change in motion. It resists acceleration. It makes it hard to get going and hard to stop once you are going. It creates the sensation of weight. This invisible ocean perspective completely shifts our place in the cosmos. We tend to think of ourselves as distinct entities, separate from the space we occupy. We say, "I am here and the space is there," but if the Higgs field is everywhere, then there is no separation. You are permeated by the universe. The field is inside you. It is threaded through your DNA, through your cells, through the very atoms that make up your brain. You are not an object sitting on a stage. You are a localized disturbance in the fabric of the stage itself. Why is this field so mysterious? Why did it take us so long to find it? Because it is perfectly uniform. Human beings and our scientific instruments are designed to detect change. We notice a light turning on. We notice a sound starting. We notice a temperature drop, but we are terrible at noticing things that never change. Think of the air pressure in this room. 14 pounds of pressure are pressing on every square inch of your skin right now. It is a heavy weight, but you don't feel it. You don't scream, "Oh no, the atmosphere is crushing me." Why? Because the pressure is constant. It is inside you and outside you. It is balanced. You evolved in it. You only notice the air when it changes, when a wind blows, or when your ears pop on an airplane. The Higgs field is the ultimate constant. It has the exact same value everywhere in the universe. It never changes. It has no wind. It has no currents. It is a perfectly still, perfectly flat ocean. Because it is so perfect, it is invisible. It creates no contrast. The only way to prove it exists is to break the stillness. We have to slap the surface of the molasses so hard that a droplet flies up. That droplet is the Higgs boson. The particle is just our way of proving the ocean is there, but the particle dies instantly. The ocean remains. This concept of the non-zero vacuum is one of the most unsettling ideas in physics. It suggests that nothing costs energy. In a normal system, nature seeks the lowest energy state. A ball rolls to the bottom of the hill. Heat dissipates until things are cold. We would expect the universe to want to be at zero energy, empty, void, and fieldless. But the universe chose a different path. It chose to fill the void with this energy fluid. Why? We don't know why. We just know that if it hadn't, we wouldn't be here. The invisible ocean is the bedrock of our stability. Without this constant pressure, without this universal fluid, the fundamental particles would disintegrate into the chaos of light speed we discussed previously. The field acts as a dampener. It is a cosmic blanket that calms the frantic jittering of the quantum world, slowing things down enough for them to become real. So, the next time you wave your hand through the air, realize that you are not just moving through empty gas. On a subatomic level, your hand is wading through a dense, invisible river. The electrons in your skin are rubbing against the fabric of reality, acquiring the mass that allows you to exist. You are swimming. The earth is swimming. The sun is swimming. We are all drifting together in this vast, hidden sea that connects the furthest star to the smallest cell. But not everything swims the same way. The ocean treats everyone differently. To some, the ocean is thick as concrete. To others, it is thin as water. And to a select few, the ocean isn't there at all. This selectivity, this unfairness of the field, is what creates the diversity of the universe. It is why some things are heavy and some things are light. To understand this, we have to leave the general metaphor of the ocean and zoom in on the specific interactions. We need to go to a party, a cosmic cocktail party where the guests determine their own weight by how popular they are. This is the mechanism that builds the world. We have established that the universe is not empty. We have stripped away the illusion of the void and revealed the existence of the Higgs Field, that invisible, molasses-like ocean that fills every corner of reality. We know it is there, and we know that we are swimming in it. But this leads to a puzzling question, one that plagued physicists for decades. If this field is everywhere, and if it is uniform, why doesn't it treat everyone the same? In our universe, particles have vastly different masses. The electron is incredibly light. It is a feather. The top quark, on the other hand, is a monster. It is roughly as heavy as an entire atom of gold, despite being a single fundamental point. If the Higgs field is a single, constant ocean, why does the electron glide through it like a skipping stone, while the top quark sinks like an anchor? Why is the field so sticky for some and so slippery for others? To understand this, we have to leave the abstract world of mathematics and fluid dynamics and enter a more relatable setting. We have to go to a party. This is the famous cocktail party analogy, a metaphor so effective that it was used to explain the Higgs mechanism to the politicians who had to approve the funding for the Large Hadron Collider. It reduces the complex calculus of quantum field theory into a social experiment. Imagine a massive ballroom. The room is filled with people. These are the guests of the party. They are dressed in evening wear, holding drinks, and chatting quietly amongst themselves. They are distributed evenly throughout the room, filling the space from wall to wall. This crowd represents the Higgs field. The people are the background energy of the universe. They are waiting. Now, imagine the doors to the ballroom swing open, and nobody walks in. This is a person with absolutely zero social status. No one knows who they are. They are invisible to the crowd. Maybe they are a waiter, or someone who wandered into the wrong building. As this person walks across the room to get to the other side, the crowd ignores them completely. The guests do not turn their heads. They do not stop their conversations. They do not gather around. Because the crowd ignores this person, they can walk through the room at a sprint. They encounter zero resistance. They can change direction instantly without bumping into anyone. They are unencumbered. In the language of physics, this person is a photon. The photon is the particle of light. It carries the electromagnetic force. It has no mass. Why? Because the Higgs field does not care about it. The photon and the Higgs are strangers. They do not interact. The photon passes through the cosmic ocean without getting wet. Because it has no social interaction with the field, it is condemned to move at the absolute speed limit of the universe forever. It is the ultimate loner, and its freedom is the result of its isolation. Now, let's reset the scene. The doors open again. This time, a B-list celebrity walks in. Maybe it's a local weatherman or a minor television actor. The crowd reacts, but only slightly. A few people near the door look up and say, "Hey, isn't that the guy from Channel 4? One or two people might step forward to shake their hand. As this person tries to cross the room, they cannot run. They have to walk. The crowd creates a small amount of friction. A tiny cluster of people forms around them at each step, asking for a quick autograph before moving away. This person has weight. They have inertia. If they want to stop, they have to gently push past the few fans blocking their path. If they want to start moving, they have to push through the initial resistance. This is the electron. The electron interacts with the Higgs field, but only weakly. It is popular, enough to be noticed, but not popular enough to be mobbed. This slight interaction gives the electron a very small mass. It is just heavy enough to be trapped by an atom, just heavy enough to form the shells of chemistry, but light enough to be easily pushed around by electricity. This delicate balance, this minor celebrity status, is the reason electricity works. If the electron were more popular, if it were heavier, our power lines wouldn't work and your brain signals would be too sluggish to form a thought. Now, the doors open a third time, the room goes silent. Enter the superstar. Imagine Einstein, or Beyoncé, or the Pope walks into the room. Pandemonium. The crowd instantly abandons their conversations and rushes toward the door. They surround the superstar in a dense, tight knot of humanity. Everyone wants to touch them, speak to them, be near them. As the superstar tries to cross the room, they can barely move. They are surrounded by a massive entourage of admirers. At every step, the crowd presses in. To move from one side of the room to the other requires tremendous effort. The superstar is trudging through a human swamp. And here is the key to the definition of mass. Imagine you try to push the superstar. You can't just push them. You have to push the entire crowd that is surrounding them. You are not just moving one person. You are moving a distorted clump of the field itself. If the superstar is standing still, it is hard to get them moving, high inertia. If the superstar is already moving, it is terrifyingly hard to stop them, because that moving cluster of humanity has tremendous momentum. It would crush you. This is the top quark. The top quark is the most socially connected particle in the Standard Model. It interacts with the Higgs field with incredible violence. The field clings to it, clusters around it, and weighs it down. This is why the top quark is so massive. It is not that the quark itself is fat or large in terms of size. It is still a point particle, infinitely small. but it is wearing a coat made of the Higgs field that is incredibly heavy. Its mass is just a measure of its popularity. This analogy reveals a profound truth about the nature of reality. Mass is not intrinsic. We used to think that an electron was born with a label that said mass 0.0005 GeV. We thought it was a property contained inside the particle, like a soul. But the cocktail party tells us that mass is extrinsic. It is a relationship. It is social. The particle is empty. The mass comes from the interaction. You are not heavy because of what you are. You are heavy because of how the universe treats you. If you could somehow turn off the charm of the top quark, if you could make it socially awkward so the Higgs field ignored it, it would instantly lose all its mass and zip away at the speed of light. It would become a photon. The only difference between a heavy particle and a light one is how much the universe likes them. This social hierarchy of particles is what builds the structure of the universe. This discrimination is vital. If the Higgs field treated everyone the same, if everyone was a superstar, the universe would be a solid block of heavy sludge, unable to move or evolve. If everyone was a nobody, the universe would be a soup of radiation. The unfairness of the Higgs field is the recipe for complexity. It allows for a diversity of behaviors. It allows some things to be agile, like electrons, and some things to be the heavy anchors of structure, like quarks, in a proton. But there is a second layer to this analogy that is equally important, and it helps us understand the Higgs boson, the particle we actually hunt for. Imagine the party again. The room is full, but this time, no one enters the door. The guests are just chatting. Suddenly, a rumor starts at one end of the room. Someone whispers, "I think I heard a noise." The people near the door lean in to hear the rumor. Then they turn and whisper it to their neighbors. "Did you hear that?" The neighbors lean in. This cluster of people leaning together moves across the room. It travels like a wave. There is no celebrity. There is no external particle moving through the crowd. It is just the crowd itself clumping together and passing the clump along. From a distance, if you were watching from a balcony, this moving clump of people would look exactly like the clump surrounding the superstar. It would look like a solid object moving through the room, but it is made entirely of the guests. This clump of guests is the Higgs boson. The boson is what happens when the field interacts with itself. It is a ripple in the ocean. It is a wave in the crowd. When we smash protons together in the Large Hadron Collider, we are not creating a celebrity. We are shouting a rumor into the room. We are punching the vacuum so hard that the field vibrates, creating a temporary clump of energy. That clump is the particle we see on our detectors. This distinction is why the concept is so beautiful. The God particle is not the creator. The field is the creator. The particle is just the sound the field makes when you strike it. The particle is the rumor. The mass of your body is the celebrity effect. So, when we ask, "Why do I have mass?" the answer is that you are a collection of particles that are incredibly popular with the cosmos. Your atoms are constantly shaking hands with the vacuum, constantly engaging in a conversation with the invisible fluid that fills the room. You are dragging the universe along with you wherever you go. You are never alone, and you are never truly empty. You are defined by your connections to the void. But metaphors, no matter how good, are not proof. A story about a cocktail party is not enough to convince a physicist to spend $10 billion on a machine. We can imagine the ocean and we can imagine the party, but science demands evidence. We cannot simply assert that the field is there because it makes the math look pretty. We have to touch it. We have to prove that the ocean exists by making it splash. And to make a splash in a fluid this heavy, you need a rock, a very, very big rock, and you need to throw it with the force of a creation event. This brings us to the most difficult engineering challenge in the history of our species. We had to build a machine that could recreate the conditions of the Big Bang just to hear the whisper of the field for a fraction of a second. There is a fundamental misunderstanding that sits at the heart of the God-particle frenzy, a confusion that has been perpetuated by headlines, simplified documentaries, and the catchy nickname itself. The confusion is this: most people believe that the Higgs boson is the thing that gives them mass. They imagine that inside their atoms, there are tiny little God particles flying around, sticking to electrons and quarks like burrs sticking to a hiker's sock, weighing them down. They imagine the boson is a permanent ingredient of the universe, a building block that sits inside us, making us heavy. This is completely wrong. You do not have a single Higgs boson inside your body right now. In fact, it is very likely that there is not a single Higgs boson existing anywhere in our solar system at this exact moment. If one were to suddenly appear inside you, it would not give you mass. It would decay instantly in a burst of high-energy radiation that would shred your DNA. To understand the reality, we must make the most crucial distinction in modern physics: the difference between the field and the particle. We must separate the ocean from the splash. We have established that the universe is filled with the Higgs field, that invisible, molasses-like fluid we discussed. This is the thing that gives you mass. The field is the miracle. The field is the God element, if you must use that word. It is the permanent, omnipresent background that stabilizes existence. It is the stage upon which we walk. The Higgs boson, on the other hand, is just a temporary vibration of that field. It is not the stage. It is what happens when you stomp on the floorboards. Think of a vast, perfectly still lake at night. The water is so dark and so calm that it looks like a sheet of black glass. If you were standing on the shore, looking out, you might not even realize there is water there at all. It looks like emptiness. It looks like the void. This represents the vacuum of space. The Higgs field is there, filling the lake. But because it is motionless, it is invisible, it is undetectable. You can stare at it for 1,000 years and never see it. Now, imagine you pick up a heavy rock and hurl it with all your might into the center of the dark lake. Splash! For a brief second, the water erupts. A column of liquid shoots up into the air. Droplets fly outward. Ripples race across the surface. In that violent moment, you finally see the water. You see the liquid because you have disturbed it. You have forced the invisible background to reveal itself by concentrating energy into a single point. That splash is the Higgs boson. The boson is a quantized excitation of the field. That is the technical term, but splash is physically accurate. When we talk about finding the Higgs boson, we are not looking for a hidden object that was tucked away in a drawer. We are looking for the result of a violent event. We are trying to hit the universe hard enough to make it scream. This distinction explains why the particle is so elusive. The Higgs field is incredibly stiff. To continue our water analogy, imagine that the lake isn't filled with water, but with liquid mercury or thick, cold honey. To make a splash in water is easy. You can do it with a pebble. But to make a splash in mercury requires a sledgehammer. To make a splash in the Higgs field requires an energy concentration that hasn't existed naturally since the first moments of the Big Bang. This is why we couldn't find it for 50 years. We knew the ocean was there, the math said it had to be. and our existence proved we were swimming in something, but we didn't have a rock big enough to make it splash. We were throwing pebbles at a frozen sea, and nothing was happening. We needed a rock the size of a mountain. So, the Higgs boson is not the cause of mass. It is the proof of the mechanism that causes mass. It is the smoking gun. It is the footprint. If we can create the boson, even for a fraction of a second, we prove that the field exists. If we create the splash, we prove the ocean is real. But there is a tragedy inherent in this search. The splash is doomed. A water droplet thrown up from a lake exists for only a moment before gravity pulls it back down into the surface. It merges back into the whole. The Higgs boson is even more ephemeral. It is an unstable particle. The moment you pour enough energy into the vacuum to pop a Higgs boson into existence, it begins to die. Its lifespan is approximately 10⁻22 seconds. That is a zeptosecond. It is a decimal point followed by 21 zeros and then a 1. It is a slice of time so thin that light can barely cross the width of a proton before the show is over. This means we never actually see the Higgs boson. We cannot capture it in a jar. We cannot take a photograph of it. It doesn't live long enough to reach our detectors. When we say we discovered the Higgs, what we actually discovered was its debris. When the Higgs boson dies, when the droplet falls back down, it breaks apart into other, lighter, more stable particles. It might decay into 2 photons, or 4 muons, or a pair of bottom quarks. These debris particles fly out from the collision point and hit our sensors. We work backward. We look at the debris and say, okay, we have 2 photons here with this specific energy. If we trace their paths back, they came from a single point. And if we combine their energies, they add up to exactly 125 GeV. The only thing that could have created this specific wreckage is a Higgs boson. We are forensic detectives at a crime scene. We never saw the explosion. We only saw the shattered windows and the scorch marks. But the pattern of the scorch marks tells us exactly what the bomb was made of. This brings us back to the concept of the field's stiffness and why the mass of the boson matters so much. The mass of the Higgs boson, that 125 GeV number, is effectively a measure of how thick the molasses is. If the field were thinner, the boson would be lighter, and it would be easier to make a splash. If the field were thicker, the boson would be heavier, and we might never have been able to build a machine strong enough to create it. We occupy a Goldilocks universe. The Higgs field is just right. It is strong enough to give atoms mass and allow for the formation of stars and planets, but it is soft enough that we, with our monkey brains and metal machines, could just barely muster enough energy to create a ripple. This realization strips the God particle of its entity status. It is not a creature. It is an event. It is a transaction. It is the localized manifestation of a universal truth. Think of the sound of a clapping hand. The sound is not an object. You cannot hold a clap. The clap is the air vibrating. If the air wasn't there, you could smash your hands together all day and there would be no sound. The Higgs boson is the sound of the vacuum being struck. It proves the medium exists. This leads to a profound philosophical shift in how we view the void. If you can strike empty space and make a particle pop out, then the distinction between matter and space is an illusion. They are the same thing in different states. Matter is just knotted space. Space is just smooth matter. The Higgs boson is the bridge between the two. It is the moment the smooth becomes knotted. So, when we look at the data from 2012, We are looking at the echoes of a bell that was rung deep within the fabric of reality. We hit the universe, and it rang back with a specific note, 125 GeV. That note tells us everything we need to know. It tells us that the ocean is real, that the water is deep, and that we are indeed submerged. But knowing this required more than just philosophy. It required violence. To make that bell ring, to create that splash, we had to concentrate more energy into a single point than exists in the center of the sun. We had to build a cathedral of technology, a machine so vast and so complex that it rivals the pyramids in its ambition. We had to turn the countryside of Europe into a weapon of mass creation. We knew the theory, we knew the ocean was there, but to prove it, we had to go fishing with dynamite. And to do that, we had to build the Large Hadron Collider. The story of the Higgs is not just a story of physics. It is a story of the largest, coldest, and most powerful machine ever constructed by human hands. A machine built for the sole purpose of making a splash in the invisible sea. Throughout history, human civilizations have demonstrated a compulsion to build. When we believe in something powerful, whether it is a god, a king, or a destiny, we express that belief through stone and scale. We dragged rocks across the desert to build the pyramids of Giza to honor the pharaohs. We raised the soaring arches of Gothic cathedrals to touch the face of the divine. We constructed the Great Wall to define our borders. These structures were the ultimate manufacturing achievements of their eras, consuming the wealth and labor of generations to manifest an idea into physical reality. Today, buried 100 meters beneath the pastoral landscape of the French-Swiss border, lies the modern equivalent of those ancient monuments. It is our pyramid, it is our cathedral, but it was not built to honor a king, and it was not built to worship a deity. It was built to hunt a ghost. This is the Large Hadron Collider, or the LHC. To call it a machine feels like a frantic understatement. It is a technological beast of such staggering proportions that it challenges the very limits of what human engineering can achieve. It is the largest, most complex, and most expensive scientific instrument ever constructed by our species. If the pyramids were built to preserve the dead, the LHC was built to understand the living architecture of the universe. The scale of this facility is difficult to comprehend from the surface. Above ground, near Geneva, you see rolling green hills, farmhouses, and the snow-capped peaks of the Alps. It is a scene of tranquil beauty. But beneath your feet, encasing a loop of tunnel that is 27 kilometers in circumference, lies a ring of Promethean fire. This tunnel is large enough to drive a train through. It crosses the international border between France and Switzerland 4 times. It is a subterranean circle where humanity has decided to recreate the conditions of the Big Bang. The purpose of this Leviathan is simple in concept but nightmarish in execution. We need to accelerate protons, the tiny, positively charged hearts of atoms, to the very brink of the speed of light, and then smash them together. As we established, to make the Higgs Field splash, to create that elusive boson, we need energy, we need violence. We need to concentrate the kinetic power of a speeding freight train into a space smaller than a dust mite. To achieve this, the LHC relies on a series of superlatives that sound like science fiction. First, there is the cold. To steer a beam of protons traveling at 99.999999% of the speed of light, you cannot use normal magnets. Normal copper wires would melt instantly under the electrical current required to bend such a beam. Instead, The LHC uses 1,232 dipole magnets, each one a massive cylinder of steel and coil weighing 35 tons. To make these magnets work, they must be superconducting, they must have zero electrical resistance. This requires cooling them down to temperatures that defy logic. The vanes of the LHC are pumped full of 120 tons of superfluid liquid helium. This cools the magnets down to minus 271.3 degrees Celsius, or 1.9 Kelvin. This is colder than the void of deep space. It is colder than the surface of Pluto. It is one of the coldest places in the universe, created by mammals who evolved on the warm savannas of Africa. Inside this frozen ring, there is a vacuum. The pipes through which the protons fly are pumped out to a pressure 10 times lower than the surface of the Moon. This is necessary because if a proton were to hit a stray molecule of gas, a single atom of oxygen or nitrogen left inside the pipe, the collision would ruin the experiment. So, we have created a ring of nothingness, wrapped in ice, buried in the earth. Through this frozen void, the beams are launched. The LHC accelerates two beams of protons in opposite directions. Guided by the magnetic fields, they race around the 27-kilometer track 11,000 times every single second. They are moving so fast that the time dilation effects of relativity kick in, and time actually slows down for the protons compared to the scientists watching them in the control room. But the acceleration is just the setup. The climax is the collision. At 4 specific points around the ring, the magnetic fields are tweaked to cross the beams. The protons are forced into a head-on collision course. When they smash into each other, the energy density at the point of impact is unimaginable. For a trillionth of a second, that tiny point becomes 100,000 times hotter than the center of the Sunday. We have created the coldest place in the galaxy and the hottest place in the galaxy, just a few meters apart, inside the same machine. The collision itself is silent. There is no sound in a vacuum, but the result is a chaotic explosion of subatomic debris. This is where the eyes of the cathedral come into play. The detectors. These detectors with names like Atlas, CMS, Alice, and LHCb are not microscopes. They are caverns filled with electronics. The Atlas detector alone is 46 meters long and 25 meters high. It is roughly the size of the Notre Dame Cathedral in Paris, but instead of being filled with pews and altars, it is packed with dense layers of silicon sensors, calorimeters, and muon chambers. It weighs 7,000 tons, as much as the Eiffel Tower. Imagine a digital camera. Your phone might have a camera with 12 megapixels, capable of taking a few dozen photos a second. The detectors at the LHC are effectively three-dimensional cameras with hundreds of millions of pixels, capable of taking 40 million pictures every single second. They have to. The collision rate is so high, and the particles fly out so fast that the electronics have to make decisions in nanoseconds about which data to keep and which to throw away. If they tried to save every collision, they would fill all the hard drives on Earth in a matter of weeks. The sheer complexity of the wiring inside these detectors looks like the nervous system of a biomechanical god. Thousands of kilometers of cables weave through the structure, carrying the faint electrical signals from the particle impacts to the data centers. It is a masterpiece of precision engineering, where components the size of a building must be aligned to within the width of a human hair. And why did we build this? Why did 20 countries pool their resources? Why did 10,000 scientists from hundreds of universities dedicate their careers to this project? Why did we spend billions of dollars to dig a tunnel and fill it with ice and magnets? We did it to find a speck. We did it because the math on a piece of paper said that there must be something else. We did it because we looked at the emptiness of the universe and suspected it was full. We built a machine the size of a city to find a particle that is smaller than an atom, a particle that lives for less than a zeptosecond. There is a profound humility in this grandeur. The Large Hadron Collider is the ultimate expression of the human paradox. We are physically small, fragile creatures stuck on a rock orbiting an average star. We cannot see the subatomic world with our eyes. We cannot touch the quantum fields with our hands, and yet our minds can encompass them. We can conceive of the Higgs Field, and because we can conceive of it, we felt compelled to build a machine big enough to touch it. This machine is a testament to what we can do when we stop fighting each other and start fighting the unknown. The LHC is a place where scientists from nations that might be political enemies work side by side. Iranians work with Israelis. Russians work with Americans. Chinese physicists collaborate with their European counterparts. In the cafeteria at CERN, the borders dissolve. The politics of the surface world are rendered irrelevant by the deeper, more permanent laws of physics. The hunt for the Higgs boson unified humanity in a way that few other endeavors ever have. The engineering challenges were endless. When the machine was first turned on in 2008, a faulty electrical connection caused a catastrophic failure. Liquid helium exploded into the tunnel, ripping heavy magnets from their floor anchors and smashing them against the walls. It was a disaster. It took a year to repair. But no one suggested giving up. The stakes were too high. The question, why do we have mass, was too important to leave unanswered. They fixed the magnets. They improved the safety systems. They cooled it down again. And in 2012, they ramped the energy up to levels never before seen on Earth. The cathedral of science creates a bridge between the two extremes of existence, the infinitely large and the infinitely small. The 27-kilometer ring is the macrocosm, a structure visible from space. The collision point is the microcosm, a realm smaller than the nucleus of an atom. By connecting these two scales, we forced the universe to give up its secret. When you think of the Higgs boson, do not just think of the equation. Think of the thousands of tons of superconducting cable. Think of the liquid helium pumping through the veins of the Earth. Think of the roar of the cooling fans and the silent, terrifying speed of the proton beams. Think of the sheer brute force required to crack the vacuum open. We found the particle, yes. But in the process, we built something perhaps even more significant. We built a monument to our own curiosity. If an alien civilization were to come to Earth 1,000 years from now, long after our cities have fallen and our languages have changed, they might dig up the LHC. They would see the ring, they would see the magnets, and they would know, without needing to read a single word, that this was a civilization that wanted to know why. The discovery of the Higgs was not just a triumph of theory, it was a triumph of the hammer. We needed a hammer big enough to ring the bell of reality, and the LHC was that hammer. And when it finally struck, the sound was heard around the world. But the moment of discovery, the moment the data finally aligned, was not a moment of loud celebration, but of quiet, tearful realization in a lecture hall, where an 80-year-old man finally saw his life's work confirmed by the machine that humanity built for him. On the morning of the 4th of July 2012, the atmosphere inside the main auditorium at CERN was unlike anything usually seen in the world of academic science. Typically, physics conferences are quiet, orderly affairs filled with polite applause and dry slideshows. But this was different. This felt less like a lecture and more like a rock concert. or perhaps a religious vigil. People had slept on the concrete floor of the corridors outside the night before, just to secure a seat. The queue snaked through the building. Security guards were overwhelmed. Inside the room, the air was thick with a specific kind of tension, the electric anxiety of a community that had been holding its breath for nearly half a century. Sitting in the audience, amidst the throng of young researchers and seasoned experimenters, was an 83-year-old man named Peter Higgs. He was not a celebrity in the traditional sense. He was a quiet theorist from Edinburgh who had spent most of his life in relative obscurity. He had arrived at the auditorium without fanfare, dressed in a simple suit, looking slightly overwhelmed by the chaos around him. He was there to find out if the idea he had scribbled down on a piece of paper in 1964 was actually true, or if he had wasted his career on a beautiful mistake. The event was a seminar to announce the latest results from the Large Hadron Collider. For months, rumors had been flying. The blogs were buzzing. The two giant detector teams, Atlas and CMS, had been analyzing the debris from trillions of proton collisions, looking for that specific splash in the field we discussed earlier. But in the world of high-energy physics, you cannot just say you found something. You cannot just see a bump in the data and pop the champagne. You need proof, and not just any proof. You need a specific, brutal level of statistical certainty known as 5 sigma. To understand the weight of this moment, we have to understand what 5 sigma actually means. In science, we deal with probabilities. There is always a chance that what you are seeing is just a fluke. Random noise can sometimes look like a pattern. If you look at static on a television screen long enough, your brain might form a face. That face isn't real. It's a statistical anomaly. Imagine you are flipping a coin to determine if it is weighted. If you flip it once and it lands on heads, that proves nothing. That is 1 sigma. If you flip it 5 times and it lands on heads every time, you might start to get suspicious, but it could still be luck. That is roughly 2 sigma. If you flip it 10 times in a row and get 10 heads, the odds of that happening by pure chance are 1 in 1,000. That is 3 sigma. In many fields of science, like psychology or medicine, 3 sigma is often considered enough to publish a discovery. But particle physics is paranoid. Particle physics deals with billions of collisions per second. 1 in 1,000 chances happen millions of times a day in the LHC. 3 sigma is not enough. 3 sigma could still be a cruel trick of the universe. To claim a discovery in particle physics, you need 5 sigma. 5 sigma corresponds to a probability of 1 in 3.5 million. In our coin analogy, this is like flipping a coin 21 times in a row and getting heads every single time. It is the point where luck becomes mathematically impossible to defend. It is the point where you can look the world in the eye and say, "This is not a mistake. This is real." The seminar began. The spokespeople for the 2 experiments took the stage one after the other. First came Joe Incandela, representing the CMS experiment. He walked the audience through the agonizingly complex analysis. He showed graphs of the background noise, the messy, predictable curve of normal particle debris, and then he zoomed in on a specific mass range. There, rising out of the smooth curve of the background data, was a distinct, jagged little hill, a bump. The room was silent, but the tension was ratcheting up. The bump was located exactly where the theory said the Higgs boson should be, around 125 giga-electron-volts, GeV. But was it enough? Incandela revealed the statistics. The CMS data showed a signal with a significance of 4.9 sigma It was agonizingly close to the magic number, effectively a discovery, but technically just short of the official threshold on its own. Then, Fabiola Gianotti, the spokesperson for the Atlas experiment, took the stage. This was the crucial moment. The two teams worked independently. They did not share data. They used different detectors, different software, and different teams. If ATLAS saw nothing, the CMS result would be dismissed as a fluke. If Atlas saw a bump at a different mass, the theory would be in trouble. But if Atlas saw the exact same bump at the exact same place, the discovery would be undeniable. Gianotti presented her slides. She showed the decay channels. She showed the photon pairs. And then the final graph appeared on the screen. There it was again. The same bump, the same mass, and the number flashed on the screen. 5 sigma. The combination of the two results pushed the certainty well beyond the threshold. The probability that this was a mistake was less than 1 in several hundred million. The auditorium erupted. It wasn't just applause. It was a release of 50 years of pressure. People cheered, whistled, and stamped their feet. It was the Woodstock of physics. The data was irrefutable. We had found the keystone of the universe. But the most powerful image of that day was not the graph on the screen. It was the camera panning to Peter Higgs. The camera found him seated in the crowd. He took off his glasses. He pulled a handkerchief from his pocket and wiped tears from his eyes. His face was flushed with emotion. Here was a man who, as a young researcher in the 1960s, had been told his theory was interesting but probably irrelevant. He had been told by some that it was nonsense. He had spent decades watching others receive Nobel Prizes for work that relied on his theory, while his own particle remained a ghost. He had lived long enough to see his name become a household term, but without the physical evidence to back it up. And now, in the winter of his life, the massive machine built by 10,000 people had spoken to him. It said, "You were right." A reporter managed to get a microphone to him. With a shaking voice, Higgs simply said, "I never expected this to happen in my lifetime. It is an incredible thing that it has happened in my lifetime." That moment of tears in the auditorium represents something far profounder than just the discovery of a boson. It represents the ultimate triumph of the human intellect. Think about what actually happened here. 50 years prior, Peter Higgs and a few colleagues sat at desks with nothing but pencils and paper. They didn't have supercomputers. They didn't have the LHC. They only had the language of mathematics. They looked at the equations of the universe and saw a flaw, a missing piece that made the symmetry break. To fix the math, they invented a fiction. They wrote down a symbol for a field that nobody had ever seen. They calculated the properties of a particle that might not exist. They made a prediction based on pure logic. They claimed that the universe must work this way, not because they saw it, but because the math demanded it. Then, humanity spent half a century and billions of dollars building a machine of metal and magnets to check that math. We dug a tunnel, we cooled helium, we smashed protons, and when we finally looked at the debris, nature matched the pencil scratchings. The universe obeyed the logic of the human mind. There is a deep, almost spiritual beauty in that connection. It suggests that the universe is intelligible. It suggests that we, these tiny biological machines evolved on a savanna, have the capacity to understand the fundamental architecture of the cosmos. We can close our eyes, do the math, and see the truth before our eyes ever behold it. Peter Higgs wasn't crying because he was famous. He was crying because of the vindication of reason. He was witnessing the closing of a circle that began in his mind and ended in the detectors of the LHC. The announcement on July 4th echoed around the world. It was front-page news in every major country. For a brief moment, particle physics was pop culture, but amidst the champagne corks popping and the headlines declaring God particle found, a deeper reality was setting in. The discovery was not the end of the story. It was the end of the beginning. We had found the particle, yes. The standard model was complete. The puzzle was finished. But as physicists looked closer at the specific number that had flashed on the screen, that 125 GeV mass, the celebration began to mix with a new kind of anxiety. The particle was there, but it looked odd. It was a little too light, or perhaps a little too heavy, depending on how you looked at it. The discovery at 5 sigma confirmed that we exist. It confirmed the mechanism of mass. But it also opened a door to a room we weren't sure we wanted to enter. The specific mass of the Higgs boson carried a hidden message about the ultimate fate of the universe. The tears of joy in 2012 were about the past, about confirming what we knew, but the numbers that generated those tears were whispering something terrifying about the future. We had found the anchor of reality, but we were about to discover that the anchor might not be as secure as we thought. The triumph of 5 sigma was about to lead us into the dark territory of the doomsday equation. To understand the profound relief that washed over the scientific world in 2012, we must zoom out from the specific details of the particle itself and look at the grand mosaic into which it fits. We need to talk about the standard model of particle physics. This is a name that sounds bureaucratic and dry, like a tax form or a car manual. It is a terrible name for what is, without exaggeration, the greatest intellectual achievement of the human species. The standard model is the periodic table of the elements, but deeper, it is the catalogue of the fundamental ingredients of reality. It is the recipe book for the universe. For 40 years, physicists had been building this model. It was a painstaking construction, piece by piece, decade by decade. They found the electron, then they found the neutrino. They found the quarks up, down, strange, charm, top and bottom. They found the force carriers, the gluon that glues quarks together, the W and Z bosons that govern radioactive decay, and the photon that creates light. Every time they found a new piece, they snapped it into the mathematical grid, and every time the math worked. The model was a masterpiece of precision. It allowed us to predict the magnetic moment of the electron to 12 decimal places, a level of accuracy equivalent to measuring the distance between New York and Los Angeles to within the width of a human hair. But for all those decades, there was a hole in the center of the board. Imagine a jigsaw puzzle of a beautiful landscape. You have assembled the sky, the mountains, the trees, and the river. The picture is breathtaking. You can see the pattern, but right in the middle, in the most crucial spot, there is a missing piece. Without that piece, the picture is not just incomplete, it is structurally unsound. The other pieces are leaning on that empty space. If that hole remains empty, the entire puzzle falls apart. The Higgs boson was that missing piece. It was the keystone in the arch. The problem with the standard model before 2012 was a fatal contradiction involving the concept of symmetry. In physics, symmetry is everything. It is the guiding principle of beauty and truth. A sphere is symmetric because it looks the same from every angle. An equation is symmetric if it remains true even when you change the variables. Physicists love symmetry because it implies order. It implies that the universe is not random, but follows a perfect, elegant logic. The equations of the Standard Model were built on a foundation of perfect symmetry. In this perfect version of the mathematics, all forces were unified, and all particles were equal. It was a mathematical utopia, but there was a catch. In this symmetrical utopia, particles could not have mass. As we discussed earlier, if you introduce mass into these symmetrical equations by hand, if you just write mass into the math, the symmetry shatters, the equations break down. They start producing answers that are nonsense, like probabilities of infinite percent. So, physicists were stuck in a dilemma. The math demanded symmetry, no mass, but reality demanded mass because we exist. The universe clearly wasn't a utopia of light-speed ghosts. It was heavy, solid, and real. How could the laws of physics be perfectly symmetrical, yet produce a universe that is full of heavy, asymmetrical lumps of matter? This is where the genius of Peter Higgs and his peers came in. They proposed a solution called spontaneous symmetry breaking. To understand this, imagine a pencil standing perfectly balanced on its tip. This is a state of perfect symmetry. The pencil looks the same from every direction. It is balanced, it is beautiful, but it is unstable. The slightest breath of air, the tiniest vibration, will cause the pencil to fall. When it falls, it lands pointing in a specific direction, say, north. The symmetry is now broken. The pencil is no longer upright. It has chosen a direction. But, and this is the crucial part, the underlying laws of gravity that made it fall are still symmetric. Gravity doesn't prefer north over south. The system is asymmetric. The pencil is on the ground, but the rules are symmetric. The Higgs field is the mechanism that knocked over the pencil of the universe. The theory suggested that at the very beginning of time, just after the Big Bang, the universe was in that state of perfect, hot symmetry. The Higgs field was zero. All particles were massless. The forces were unified. It was the mathematical utopia. But as the universe expanded and cooled, the Higgs field became unstable like the pencil on its tip. It couldn't hold that zero value. It fell. It rolled down into a lower energy state, filling the vacuum with the energy molasses we talked about. When the field fell, it broke the symmetry. It distinguished the heavy particles from the light ones. It separated the weak nuclear force from the electromagnetic force. It shattered the perfection of the early universe to create the complex, structured, massive reality we live in today. This was the theory. It was elegant. It solved the mathematical problem perfectly. It allowed the equations to remain symmetric on paper while explaining why the world looks asymmetric to our eyes. But for 50 years, it was just a story. A just-so story. We had no proof that this pencil falling event ever happened. We had no proof that the field existed to break the symmetry. This is why the discovery in 2012 was so much more than just finding a new particle. It was the vindication of a worldview. When the LHC detectors captured the Higgs boson, they didn't just find a new speck of dust. They proved that spontaneous symmetry breaking is real. They proved that the universe did undergo a phase transition billions of years ago. They proved that the vacuum is not empty, but filled with a potential that shapes reality. If the Higgs had not been found, or if it had been found at a mass that didn't fit the theory, the Standard Model would have collapsed. We would have been forced to admit that our fundamental understanding of nature was wrong. We would have had to tear up the textbooks and start from scratch. The 10 billion machine would have been a monument to our ignorance. Instead, the piece fit. It fit perfectly. When the data came in, the properties of the Higgs boson matched the predictions of the standard model with uncanny precision. It had zero spin. It had positive parity. It coupled to other particles exactly in proportion to their mass. Heavier particles interacted with it more, lighter particles less. It was behaving exactly as the architect of the standard model should behave. This moment cemented the standard model as the most successful theory in the history of human thought. Think about what that means. We, a species that has only had electricity for a few hundred years, have successfully mapped the interactions of the fundamental components of the universe. We have a grid of 17 particles that explains everything from the burning of the sun to the chemistry of your DNA to the structure of a neutron star, and the Higgs was the final checkmark on that list. However, there is a strange irony in this victory. In science, you almost want the puzzle piece not to fit perfectly. You want it to be a little bit jagged. You want it to be a slightly different color. Why? Because cracks in a theory are where new discoveries come from. If the model is perfect, there is nowhere left to go. The Higgs boson we found was almost too perfect. It was exactly what the simplest version of the theory predicted. It didn't have any exotic companions. It didn't show signs of a deeper underlying structure. It was just there. It did its job, completed the puzzle, and went silent. This led to a feeling of post-discovery depression among some theorists. They had hoped the Higgs would open a door to new physics, to dark matter, to supersymmetry, to extra dimensions. Instead, it seemed to close the door on the 20th century without giving us a clear hint of what the 21st century of physics should look like. It was the final brick in the wall, and now we are staring at a completed wall, wondering what is on the other side. But there was one detail, one specific number that kept the physicists awake at night. While the Higgs fit the model, its mass, that number of 125 GeV, sat in a very uncomfortable range. It wasn't too heavy, and it wasn't too light. It was right in a weird valley of stability. When you plug the mass of the Higgs boson and the mass of the top quark into the equations that govern the stability of the vacuum, you get a result that is deeply unsettling. The equations suggest that the pencil of the universe didn't fall all the way to the ground. They suggest that the pencil is stuck on a ledge. The standard model is complete, yes, but the picture it reveals is not one of eternal stability. It is a picture of a universe that is balancing on a razor's edge. The final piece of the puzzle revealed that the puzzle board itself might be fragile. This leads us to the dark twist in the tale of the Higgs discovery. We set out to find the particle that gives us life, the particle that allows for structure and existence, and we found it. But in finding it, we also found a prophecy of our own destruction. The victory of the standard model unlocked the door to the concept of vacuum decay. It turns out that the God particle might have a sinister alter ego. The field that holds us together today could, in the distant future, be the very thing that tears us apart. The architecture of reality is verified, but the inspection report has just come back, and the foundation is cracked. The story of the Higgs boson usually ends with applause. We built the machine, we found the particle, we confirmed the theory, and we gave Peter Higgs his Nobel Prize. It is a narrative of triumph, a clean and happy ending to a 50-year mystery. But in the back offices of theoretical physics departments, away from the television cameras and the public celebrations, the discovery of the Higgs boson unlocked a different kind of story. It is not a story of creation, but of uncreation. It is a story that stems directly from the specific numbers we found in the debris of the Large Hadron Collider, and it leads to a concept so terrifying that it makes the heat death of the universe look like a gentle sunset. We have arrived at the dark twist in our journey. We have arrived at the doomsday equation. To understand this, we have to go back to the idea of the Higgs field as a fluid filling the universe. We established that this field has a non-zero value it is on. It sits at a certain energy level, providing the resistance that gives particles their mass. We assume, naturally, that this current state is the bottom of the well. In physics, everything seeks the lowest possible energy state. A ball rolls down a hill and stops at the bottom. Water flows to the lowest point. Heat dissipates until it is cold. We exist because the Higgs field rolled down from the high energy of the Big Bang and settled into its current value. We assume this resting place is the absolute floor of reality, a state physicists call the true vacuum. If we are in the true vacuum, we are safe. The ball is at the bottom of the valley. It has nowhere lower to go. The laws of physics are locked in, stable, and eternal. But the data from 2012 whispered a different possibility. When physicists took the measured mass of the Higgs boson, 125 GeV, and combined it with the measured mass of the top quark, and plugged those two numbers into the equations that govern the stability of the vacuum, the math spat out a disturbing result. The numbers suggest that we are not at the bottom of the valley. The equations imply that the Higgs field is stuck on a ledge. Imagine a hiker descending a mountain in a thick fog. He walks down the slope until the ground levels out. He stops, sets up his tent, and assumes he has reached the valley floor. But he hasn't. He is actually camped on a narrow shelf, a plateau halfway down the mountain. Below him, hidden by the fog, is a cliff that drops down to a much deeper, much lower valley. This precarious state is called a false vacuum, and the specific term for our situation is metastability. We are stable, for now the shelf is solid enough to hold our tent, but we are not ultimately stable. There is a lower state of energy that the universe would prefer to be in. The universe is holding its breath. It is balancing on a tightrope, and the laws of quantum mechanics tell us that nothing balances forever. This leads us to the mechanism of the end, quantum tunneling. If this were classical physics, we would be fine. A ball sitting on a shelf won't move unless someone kicks it. But in the quantum world, particles and fields don't have to climb over a barrier to get to the other side. They can tunnel through it. There is a non-zero probability that the Higgs field, at any random point in the universe, could suddenly notice that there is a lower energy state below it. It could effectively slip through the floor of our reality and crash down to the true vacuum. If this happens, it won't happen everywhere at once. It will start at a single point, a single spark, somewhere in the dark void of space, perhaps billions of light years away, or perhaps right next to Earth. A tiny bubble of the true vacuum will form. This bubble is the executioner of the cosmos. Inside the bubble, the Higgs field has dropped to a new, lower value. This means the laws of physics inside the bubble are completely different from the laws outside. The constants of nature change. The mass of electrons and quarks changes. Chemistry, as we know it, becomes impossible. Atoms cannot hold together. Matter collapses or disperses. The very fabric of space-time inside the bubble is fundamentally rewritten, and the bubble grows. Because the energy state inside the bubble is lower than the outside, the bubble releases energy as it expands. This energy feeds the expansion. The wall of the bubble accelerates outward instantaneously, reaching the speed of light. It becomes a sphere of total negation, expanding at the absolute cosmic speed limit, devouring the old universe and replacing it with the new, dead physics of the true vacuum. This is the nightmare of vacuum decay. It is not an explosion in the traditional sense. An explosion is a movement of matter through space. Vacuum decay is a transformation of space. The most terrifying aspect of this scenario is the stealth of it. Because the bubble wall expands at the speed of light, no information can travel faster than it. You cannot see it coming. If such a bubble began inside our sun right now, we would not see the sun go dark. We would not see a warning flare. The bubble would hit us at the exact same instant that the light from the event reached our eyes. One moment, you are reading this text, existing as a biological entity held together by the current laws of physics. The next moment, you are simply gone. There is no pain. There is no time for neurons to fire a signal to the brain saying something is wrong. The chemical bonds that hold your molecules together would be undone before the electrical impulse of fear could cross a synapse. It is the ultimate, instant, painless uncreation. We would not be killed. We would be deleted. This brings us back to the numbers. Why do we think this is possible? It comes down to a cosmic tug-of-war between the Higgs boson and the top quark. In the equations of the Standard Model, the Higgs boson tries to make the vacuum stable. It wants to keep the tent on the shelf. The top quark, because it is so heavy, tries to destabilize the vacuum. It wants to drag the tent off the cliff. If the Higgs boson were heavier, say 130 GeV, it would win the fight easily, and the universe would be absolutely stable. If the Higgs boson were lighter, say 115 GeV, the top quark would have won long ago, and the universe would have collapsed billions of years in the past. We never would have evolved to ask the question. But nature, with a dark sense of irony, landed right in the middle. The measurement of 125 GeV puts us exactly in the metastable zone. We are in the Goldilocks zone of doom. We are just stable enough to exist for billions of years, allowing life to evolve, stars to burn, and civilizations to rise, but not stable enough to last forever. We are living on borrowed time. It is a profound psychological shift. For centuries, we looked at the stars and imagined them as eternal. We thought of the void as a neutral, safe backdrop. Now, we look at the vacuum and realize it is a loaded gun. The space in front of your face is potentially combustible. The very thing that gives us mass, the field that anchors us to reality, carries within it the seed of our undoing. The God particle is a double-edged sword. It creates the structure of the universe, but it holds the trigger for its reset. However, before we succumb to existential dread, we must look at the timescales. Quantum tunneling is a probabilistic event. The probability of the Higgs field tunneling through the floor in any given year is infinitesimally small. When physicists calculate the expected lifetime of a metastable universe like ours, the number they get is a 1 followed by 100 zeros years. This is a timescale so vast it renders the word forever almost meaningless. It is far longer than the time it will take for the sun to burn out. It is longer than the time it will take for all the stars in all the galaxies to fade into darkness. In all likelihood, the universe will die a slow, cold death of entropy long before the vacuum decides to snap. We will almost certainly not be around to see the bubble. But almost certainly is not certainly. That is the haunting part. In a quantum universe, unlikely things happen. They are rare, but they are possible. There is a non-zero chance that it could happen 1 billion years from now, and a non-zero chance that it started 5 minutes ago in the Alpha Centauri system. And the wall of death is currently rushing toward us at 300,000 kilometers per second. There is also a question of whether we could accidentally trigger it. This was a fear raised by the media when the LHC was first turned on. Could smashing particles together at such high energies create a localized bubble of true vacuum? Could we accidentally nudge the hiker off the ledge? The answer from the scientific community is a confident no. The universe is a far more violent place than the Large Hadron Collider. High-energy cosmic rays particles from deep space have been smashing into the Earth's atmosphere and the surface of the Moon for billions of years, with energies far greater than anything the LHC can produce. If high-energy collisions could trigger vacuum decay, it would have happened already. The fact that we are here is experimental proof that our atmosphere is safe from our machines. Yet, the concept remains. It hangs over the standard model like a dark cloud. It reminds us that our understanding of stability is an illusion. We think of the ground beneath our feet as solid, but on a quantum level, the ground is resting on a trapdoor. This discovery adds a layer of fragility to the beauty of the cosmos. It tells us that the laws of physics are not necessarily written in stone. They might just be a temporary arrangement, a phase the universe is going through. We are the beneficiaries of a cosmic accident, a temporary balancing act that has allowed complexity to flourish on the edge of a precipice. The doomsday equation is not a prediction of inevitable fire and brimstone. It is a revelation of our contingency. It tells us that existence is not a guarantee. We are here because the field is stuck. We are here because the symmetry broke in a specific way and got caught in a local minimum. We are the children of a quirk in the potential energy graph. And perhaps there is something beautiful in that fragility. If the universe were perfectly stable, it might be static, eternal, unchanging. But a metastable universe is a dynamic one. It is a universe that has a history and, potentially, an end. It makes the time we have, the time where the laws of physics allow for stars and carbon and consciousness, feel incredibly precious. We are surfing a wave that might one day crash, but for now, the wave is holding and the view is spectacular. So, the Higgs Boson gave us the final piece of the puzzle, and the picture it revealed was a cliff edge. We are standing on that edge, peering into the abyss of the true vacuum, marveling that we haven't fallen yet. And now, having faced the possibility of the ultimate end, we must conclude our journey. We must step back from the terror of the void and look one last time at the architect itself. We must synthesize everything from the goddamn nickname to the invisible ocean to the cathedral of ice to the bubble of doom to understand what this particle really means for the human experience. We have journeyed through the subatomic underworld, past the smash of protons and the freeze of liquid helium, to arrive at the end of our story. We started this exploration with a nickname that physicists hate: the God particle. It was a name born of marketing and frustration, a sensational headline designed to sell books. But as we have peeled back the layers of the standard model, we have realized that while the name might be scientifically inaccurate, it was poetically accidental. We didn't find a deity in the machine. We didn't find a bearded man controlling the cosmos. But we did find the architect. We found the silent, invisible, omnipresent force that holds the blueprint of reality together. To conclude this saga, we must step back from the specific details, the 125 GeV mass, the 5 sigma statistics, the dipole magnets, and look at the philosophical picture they have painted. We have effectively rewritten the definition of what it means to be here. For thousands of years, humans have operated under the assumption of atomism. We believed that the universe was made of hard, distinct objects separated by empty space. We thought that a rock was a rock, and the space around it was nothing. We thought that we were isolated entities moving through a passive void, but the Higgs discovery has shattered that illusion. It has taught us that the void is not passive. The void is not empty. The void is alive. We now know that the space between your eyes, the space between the stars, and the space inside your atoms is filled with a thick, energy-rich fluid. We know that this fluid, the Higgs field, is the only reason anything has form. Think back to the world of light speed we imagined at the beginning. Without the Higgs, the universe is a frantic, blurry mess of radiation. There is no structure, only speed. There is no time, only the eternal now of the photon. In that world, nothing can hold hands, nothing can build. It is a universe of absolute freedom, but it is a freedom that prohibits existence. The Higgs field is the great compromiser. It is the friction that imposes order on chaos. It is the cosmic brake pedal that slows down the wild, flighty particles of the quantum world and forces them to settle down. It forces them to become heavy, and in that heaviness, they find the ability to bond. Because they are slow, they can click together to form protons. Because they are heavy, they can attract electrons to form atoms. Because they are atoms, they can link up to create molecules and proteins, and eventually, the complex biological machinery that allows you to sit there and listen to these words. This leads to a profound realization. You are not a static object. You are an event. We tend to think of our mass as a property we own, like the color of our eyes or the length of our hair. We think, I weigh 70 kilograms. But physics tells us that mass is not a possession, it is a transaction. It is an active, ongoing relationship between the particles that make up your body and the field that fills the room. Every single nanosecond, the quarks and electrons in your body are trying to fly apart at the speed of light. That is their nature. That is their desire. But every single nanosecond, the Higgs field is grabbing them, slowing them down, and granting them the heft required to stay put. You are being created continuously. You are a localized knot of resistance in the flow of the universe. If the field were to stop interacting with you for even an instant, you would explode into a burst of light. This makes the concept of emptiness obsolete. We are never alone. We are never truly separated from the universe. We are swimming in it. We are connected to the furthest star not just by gravity, but by the fact that the star is swimming in the same ocean we are. The fabric that slows down the hydrogen atoms in the core of the sun is the exact same fabric that slows down the atoms in your fingertips. We are united by the medium of our existence. The discovery of the Higgs boson also stands as the ultimate testament to the power of the human mind. It is a story of incredible hubris and incredible humility. Consider the timeline. In 1964, Peter Higgs and his colleagues looked at the math of the universe and saw a flaw. They didn't see the particle. They saw a logical inconsistency. To fix it, they invented a ghost. They wrote down an equation for something that nobody had ever seen, simply because the logic demanded it. They predicted that the invisible ocean must be there. And then we waited. We waited while technology caught up to imagination. We waited while nations argued and budgets were cut. We waited while we built the cathedral of science, the Large Hadron Collider, a machine so complex it rivals the biological complexity of a living organism. And when we finally turned the key, when we finally struck the vacuum with the force of a thunderbolt, the ghost appeared. The universe answered us. It said, yes. It is rare in the history of our species that we get such a clear answer. Usually, science is messy. It is full of contradictions and revisions. But the Higgs discovery was a moment of perfect alignment between the inner world of human thought and the outer world of physical reality. It proved that the universe is intelligible. It proved that with enough mathematics and enough engineering, we can touch the fundamental bedrock of nature. We can predict the architecture of the cosmos before we even see it. But, as we discussed with the doomsday equation, this knowledge comes with a price. We learned that the architect is not necessarily building for eternity. We learned that the field that gives us life is balanced on a razor's edge. The specific mass of the Higgs boson, that 125 GeV number, whispers to us that the universe is metastable. The ocean we swim in might one day drain away, or freeze over, or change its state entirely. This could be seen as a source of despair. It could make our existence feel fragile and temporary. But there is another way to look at it. A statue carved from stone is beautiful because it endures. But a house of cards, or a melody, or a sunset is beautiful precisely because it is temporary. It is beautiful because it requires a specific, delicate balance to exist at all. The metastability of the Higgs field tells us that we are the lucky ones. We are living in the Goldilocks era of the universe. We are living in that rare, precious window of time where the laws of physics allow for complexity. We are balancing on the tightrope, and the view is magnificent. The Higgs boson is the anchor of this reality. It is the pin that holds the wheels of the universe on the axle. Without it, there is no us. There is no here. There is only the rushing wind of the photon. So, while it may not be God, it is certainly the closest thing to a creator that physics has ever found. It is the giver of substance. It is the granter of form. As you go about your life, walking through the air that feels empty, remember the ocean. Remember that your weight, the pressure of your feet on the floor, is the result of a cosmic conversation happening deep within your atoms. Remember that you are solid only because the universe is holding you tight. You are a ripple in the invisible water, a brief, beautiful splash of consciousness in a universe that wants to be light. We have peeled back the curtain and seen the gears of the machine. And the machine is stranger, colder, and more magnificent than we ever dared to imagine. We have found the limit of the visible, and in doing so, we have learned to see the invisible. Thank you for taking this journey into the heart of the Standard Model, from the smallest equation to the largest machine on Earth. It has been a long trip down the rabbit hole. Sleep well, and dream of the invisible ocean. I'll see you in the next video.